So in this video, we'll be going over the different units for the upcoming AP Physics C Mechanics exam. We'll go over sample problems and formulas. So the first thing we're going to go over are the four major kinematics. So it's going to start off with your first one, which is derived from just your acceleration. You have acceleration is equal to the change in velocity over the change in time. Well, that's just your final velocity minus your initial velocity over the change in time. And assuming your time starts at 0, that's just your final velocity minus your initial velocity over that point in time. Multiply both sides by the time, you get your final velocity minus your initial velocity is equal to your acceleration times the time, and then your final velocity is equal to your initial velocity plus the acceleration times the time. And that is your first kinematic equation. The next one is going to be your first displacement. Their first displacement equation. So that's going to be your displacement is equal to the average velocity times the time. Alright? Which is the same thing as your final velocity plus your initial velocity divided by 2 times the time. This is your average velocity. Your other displacement we're solving for, and that's going to be your displacement is equal to your initial velocity times the time plus half of the acceleration times the time squared. We're not going to go over the final velocity times the time minus, we're not going to go over that one. You can see that one on my website, but it's barely ever used. It's basically negligible, like air friction, or just friction in general, except for in this class. But you'll have your one that is derived from your conservation of energy, which is final velocity squared minus your initial velocity squared is equal to 2a delta x. Work is equal to F d, right? Let's assume that we're going like this. So cosine theta is going to be 1, right? Because we're going in the direction of the force that we want. All of these are going in the same direction is what we're assuming for the kinematics. And that's equal to the change in the kinetic energy. So that's going to be 1/2 mv final squared minus 1/2 mv initial squared is equal to the force, which is ma, times the distance, which is going to be your displacement. Cancel out the m, multiply everything by 2, v final squared minus v initial squared is equal to 2a delta x. Just like that. Now let's go over a few problems related to kinematics. So the first thing we're going to do is we're going to go over terminal velocity. So what you're going to have is you're going to have your diagram here. There's two forces on it. Okay? You have your drag force. Don't worry about what forces are at the moment. We're just describing things that relate to kinematics and things like that. And one of the things that does relate to it is terminal velocity, which is originally just a simple way of calculating acceleration and things like that. But now we're accounting for drag force and air resistance. And that is equal to some constant of proportionality, we'll call it beta, times the velocity. Now, it could be anything. It could also be the velocity squared, right? But it's always proportional to to the velocity in some way. Either the velocity squared, velocity cubed. You'll see a bunch of different ways it can be represented on the test. But for this one, we'll stick simple and just go with beta v. And then you have your weight, mg. Simple. So at terminal velocity, your drag force is equal to your weight. So that just means that mg is equal to beta v. So we'll say v sub t for terminal. So that means v sub t is equal to mg over beta. Is how to derive the equation for velocity. Well, our sum of forces is just your weight, because we're going downwards, minus that drag force, okay? And that is equal to the mass times the acceleration. Okay, we'll learn more about that later. But we can turn this into a differential equation because the acceleration is the derivative of the velocity with respect to time. So that just gives you m times dv over dt, though depending on whether your velocity is given as a function of time or not, or a function of multiple variables, it might be partial v over partial t, but for now we'll stick with dv over dt. We'll get more into partial later when we see derivatives of multiple variables, such as 3xy. You take the partial derivative of f, you take the partial derivative of this with respect to x, you assume y is just like some constant, and then that just gives you 3y. M times dv over dt, your derivative of velocity with respect to time, or acceleration, is equal to your mg minus beta v. Alright, move variables to the right spot. Now, actually, derivatives like this are not fractions, but when we're dealing with differential equations, if we want to, we can treat it like a fraction. Now, we take the integral of both sides. Your limits are going to be 0 to v, starting from rest, going up to our velocity that we're trying to solve for, starting with time 0, ending with time t. So 0 to t, 0 to v. This will give us our function v of t, so our velocity at some point in time. So first thing we're going to do is we're going to cancel these and divide this by m. This easily just integrates to t. That's pretty simple. This integrand is going to be a little bit different. It's going to be a little hard. So we're going to go over u substitution. So you have some variable u that's equal to some expression here regarding with v. That will be g minus beta over mv. Take the derivative of both, du over dv, right? Take the derivative of u with respect to v. That's going to be g, well, the derivative of g is 0, so that g cancels out. We're left with negative beta over m, okay? Multiply both sides by dv. And now you have du is equal to negative beta over m dv. Multiply both sides by negative m over beta. And dv is equal to negative m over beta du. So now we plug that in. So t, our time, is equal to the integral from, now we need to plug in 0 and v into our u to change the limits. So u is equal to g minus beta over m times 0, so that's just g. And g minus beta over m times v, so that's just going to, with v subbing in, so that's g minus beta over m v, right there. Okay? Let's move the t equals to right there. The next thing is we're going to plug in that negative m over beta du, so we have negative m over beta right here. Now, that's 1 over this, that's u, so that's 1 over u, and then we plug in our du. Then just solve for v, and you get v of t, your function right there, is equal to mg over beta times 1 minus e to the negative beta over mt. Let's derive our range formula and then solve the question. So determine the distance traveled by a cannonball. So it starts on the ground, right? Shot by a cannon at an angle of 15 degrees from the horizontal, from the horizontal with a speed of 10 meters per second. Assume the initial height is 0. Already done. So the range is how far it goes to reach the same height, right? So that's going to be our range right there. So find the distance of how far it traveled. Well, first thing we're going to do is we're going to use one of our kinematics. Delta. We know that our initial speed is 10 meters per second, and that the angle from the horizontal is 15 degrees. That's definitely not 15 degrees, but don't worry about it. So we have delta y, the change in our height, is equal to the initial velocity with respect to y, or if you want to be more particular, you could just say the initial velocity vector dot j to get the y value, times the time plus the half of the acceleration in the y direction times the time squared. First thing we need to do is we need to define positive and negative. We're going to say that our acceleration is in the negative direction, so down is negative, up is positive. So delta y is going to be equal to what? Well, we know that a sub y is going to be equal to negative g. So that's equal to v initial times sine theta. We're not going to sub in anything until we derive our range formula, times the time, minus 1/2 gt squared. Alright? The next part of this is now we solve for t, because our height is actually 0, because our change in height is 0 throughout the entire range. Then we solve for t. Well, t is going to be equal to 2 over g v naught sine theta, or 0. 0, but we will care about the time at which it ends, not the time at which it starts at that position. We want to find the time at which the second time that it reaches that position. Right, so that's going to be 2 over g v naught sine theta. Then we're going to plug that in to delta x, which is our distance in the horizontal, is equal to v sub x, the horizontal velocity, which is always going to be, in terms of projectile motion, going to be constant because there's no force interacting with it, so it's going to be at a constant velocity. The only acceleration that we have is in the y direction, so we don't need to worry about the x direction. So there's no initial or final, it stays constant. Times the time. Okay, we know the time here. We're not given the time, so we can't solve for it, right? So we can't, just plug it into this equation and say we're done. But that's going to be delta x is equal to v naught cosine theta. That's what v sub x is, the x component. Or, if you want to be technical, yes, it's v naught dot I, right? Because that's the same thing as the, right, I, because it's the same thing as the magnitude of your initial velocity vector. That's just 1, because it's 1, 0, 0, or 1, 0, 0, however many dimensions you have in your system. So that is always going to be 1, that's a unit vector, and then times cosine theta, which is the angle between them, those two vectors, which is how we derive this. V naught cosine theta times the time, which is 2 over g v naught sine theta. First thing we notice is that we have cosine theta, 2, and sine theta. That is an easy indication that we have sine of 2 theta. So that's just v naught squared, okay, sine 2 theta over g. That is your range formula right there. So now let's plug in what we know. We know our initial speed and we know our angle. V naught is 10, 10 squared is 100, 100 divided by 10, because we have g, is 10. Sine of 2 theta, well, sine of 30 is 1/2, so that's 10 divided by 2, so that's 5. So our range is 5 meters. And that's how you get the range formula and what it is. So if you're only given the initial velocity and the angle from the horizontal, just plug it in there if you need to find the horizontal distance. Simple as that. We're on to the next unit, Newton's laws and motion. First thing you're going to need to know, Newton's law here. The sum of the forces in a system is equal to the mass times the overall acceleration. Next thing is gravitation. You need to know Newton's law of gravitation. That equation is pretty simple. That's just your force of gravity is equal to your gravitational constant g times the mass of one object, the mass of the other object in the system, divided by the radius, which is just the distance between the centers of mass. Don't know why that's represented using r. It would make more sense if it was represented using d. But I guess when you take the derivative of the equation, I guess dd doesn't really make that much sense. So we have a sample problem for this one. That one is Determine the escape velocity of a satellite with mass m leaving orbit from 5.5 times 10 to the 6 meters from the Earth's center of mass. The mass of the Earth is 6 times 10 to the 24 kilograms, and g is 6.67 times 10 to the negative 11 meter cubed per kilogram second squared. Well, all we really need to know here is that our potential energy, okay, our gravitational potential energy is equal to the negative integral, of f sub g dr. There you go, there's your integral with dr instead of dd. But yeah, and that is just going to be g m1 m2 over r. Alright, then we know that our kinetic energy, which escape velocity means when all of that potential energy is converted into kinetic energy, which means that you're infinitely far away. 1/2 mv squared is equal to g assuming that there was no kinetic energy in the system to start, right, is the point of this, over r. Okay, v sub e for escape velocity. What m is this? Well, that's the mass of the satellite, so that's going to be m2. What's m1? Well, that's going to be the mass of the Earth, so we're going to say that this is g me, right? And it's a mass m, so we're just going to say m here, over r. Okay? First thing we know is we know m can cancel. Now we just solve for v sub e. That's relatively simple. It's just the square root of 2g me over r. Plug in your values and you get 1.2 times 10 to the 4th meters per second. The first one is a car is traveling a maximum constant speed of 10 meters per second around a circular track without skidding, which means that it doesn't slip, right? So that means it's a constant motion. And it's a constant speed, so we know that it is circular motion. An identical second car travels around the same track without skidding but has 4 times the centripetal acceleration. What is the maximum speed of the second car? This is actually a very simple question. The acceleration of the second car is 4 times the acceleration of the first. Well, in centripetal acceleration, a sub c, the centripetal acceleration, is v squared over r. Since they're on the same track, r is the same. So we can cancel out the r's here. So that's just going to leave you with v2 squared is equal to 4 times v1 squared. So then you just take the square root and you're left with v2 is equal to 2v1. So it's going to be 20 meters per second. The next question is a cart of mass m on a roller coaster track with initial velocity v0 from height h. Let's draw this. Okay. Okay. It has an initial velocity v0. Okay. It says, later in the track there is a loop with radius r. If the loop starts from height 0, so like this, the r could be larger than h, we don't know. So that'd be a pretty stupid design if there's no booster or anything like that, if it's solely based off of physics concepts, but let's not worry about that. With radius r, okay? Then what is the minimum initial velocity required for the cart to clear the loop? Assume no friction. 3 greatest words you'll ever hear. Solve for v0 in terms of r, h, m, and physical concepts. Alright, so we're going to pull from in the future energy, starting with our initial energy, ending with the same energy. No friction, so there is no force taking away energy from the system. So conservation of energy. So our initial energy is we have kinetic and potential energy at the beginning, not just potential energy because we're moving at the start. That's going to be 1/2 m, because the mass is m, v v0 squared plus mg times the initial position height is equal to the same as the energy here. That is going to be 1/2 mv. The velocity in the loop is going to be, we're going to call that C, VC, right, squared, plus the potential energy mg 2r. All right, because it's a height of 2r from the ground at the highest point. The next thing we're going to do is we're going to look at here the forces. Now we're looking at minimum velocity, which means that at that point the normal force from the track is 0. Okay, we're looking for minimum velocity required. So that means that our sum of forces is just going to be mg, just the weight. No friction, so we don't need to worry about anything in multiple directions or anything like that. All one direction, downwards. We're going to say down is positive, I guess, for this system. It doesn't really matter though, because we're looking for speed, not, because v squared is always positive, so you're never going to get a negative value for your acceleration anyways in a circular motion. I digress though. mg is equal to ma sub c. A sub c is the same thing as v sub c squared over r. Okay, so mg, well, we can cancel out the m. V sub c squared over r is equal to g. Okay, so v sub c is equal to the square root of gr. All right, next step. Plug that in there. M's cancel out. Multiply everything by 2. V naught squared plus 2gh is equal to v sub c squared plus, multiply everything by 2, so that's 2 times 2, 4, 4gr. We'll plug this in, you get gr. So that's going to give you 5gr. 5g, oh no. Then we're solving for v naught. So v naught squared is equal to 5gr minus 2gh, which is the same thing as take away the g. 5r minus 2h. Take the square root. V naught is equal to the square root of g times 5r minus 2h. There you go. Our question here says an electric motor spins a pulley with a spool of string with negligible mass. Okay, so we don't need to worry about that. The string is connected to a hanging mass m. What is the power needed to lift the mass a distance d starting from rest in time t with constant acceleration? Ignore rotational inertia from the pulley. Yes, don't need to worry about that rotational inertia. We'll get into that later. That's going to be a large portion of time because it's integrals. But yeah. So let's draw that out. A spool with a block mass m. A motor is attached here. Find the power of the motor required to do this. Well, there's no constant velocity, so we can't just do, well, it's force times velocity. But we don't know the force, because the force is the tension minus the weight. We don't know what the tension force is, because it's not moving at a constant velocity. So the acceleration isn't 0, so we can't say t is equal to mg, right? And therefore we can also not do fv. So p is not equal to fv in this case. It just isn't. But in this case, what we're going to do is we're going to say, well, work is equal to force dot distance, right? Well, in this case, our angle is negligible because we're going to say that this is the 0 degree point. We're going to say that this direction is 0 degrees. So the angle between the vectors there is 0. So cosine of theta is 1. Magnitude of the vectors are just going to be fd, so we're just going to have force times the distance. Now what is our force? Well, that's the net force. That's T minus mg. We don't know what T minus mg is, but we know that net force, based off of what we learned last unit, Newton's laws, is the net force is equal to the mass times the acceleration. So that's going to be ma, so your work is equal to ma, right, which is times the distance traveled, which is d. And it did that within a span of time t. It starts at rest. So you know your velocity is changing. That automatically tells you that it's not at a constant velocity either. Next thing is, now we just need to put this in terms of time because we need to take the derivative of our work in terms of time. We don't know the acceleration, so we need to get something that we do know, which is our distance. So we take the second derivative. So this is what? second integral, my bad, not derivative. Then we're going to take the absolute value of that to actually get the power. That's going to give you 4m d squared over t cubed. Linear systems. Now, this is going to be where I include a lot of multivariable things because they actually really help. And that is going to be triple integrals. So, your center of mass is represented using x bar, y bar, and z bar. All right. Where, okay, stay with me on this one. X bar is equal to the integral over some space d, x times the density in terms of x, y, and z with respect to the volume. And that's 1 over the mass. And what is that m? Well, it would be easier if I just show it in integral form. That is going to be your your volume of the region with respect to d, which is why we have dv. And then take away the x, and it's just x, y, z, dv. Because this is the volume of the region, right? So if you remove the density, right, the region density, if you remove the space density here, then you're just left with this dv, which just gives you the volume of the entire region that you're integrating over. And therefore, when you include the density there, you know that that's what? M over v times the velocity, which gives you m. So that's how you get m. Not velocity, times the volume, because this gives you the volume of the region, which gives you the mass. So that's how you do this here. Now, you can't just be like, because this is a function with respect to x, y, and z, so you can't do that unless it's 1. Unless it's a constant, because then that constant can be pulled out. And so therefore, you don't even need to worry about it. Right? So there's that. And it's the same thing with y, z, except replace the x with y and z, respectively. So let's go over 3 sample problems. We're going to go over linear density, surface density, or area density, and volume density. Okay? So lambda, sigma, and rho. Though they're all confined to the variable delta. Delta meaning density, dd. Derivative of d. I'm very good at making jokes. Alright, first question is, a rod with non-uniform density lambda equals 3x and length L, find the center of mass. Well, our center of mass is going to be x bar 0, 0 because we're only in one dimension. So we only need to take the first integral. No second or third integral because we're only in one dimension. Because that's going to be 0 to 1, 0 to 1, 0 to 1. Not 0, 0 to 1, and 0 to 1. And then whatever the bounds are for there. I'll find the center of mass. Bar is equal to 1 over m integral across, well, technically we only need to do one integral because we're in one dimension of space. And that is going to be from 0 to L. That's our bounds there. X times, then you have your delta x, y, your density function in terms of x, y, and z, which is lambda. And then dv is going to be dx because we only have one, are in one dimension. 1 over m times x cubed L minus 0, so that's going to be L cubed. Okay, 3 over 2 L squared. Okay, because it's just the derivative of 3x from 0 to L, so that's going to give you, 3 times 1/2 x squared from 0 to L. You can remove the 0 because it's going to give you 0, so it's going to be 3 over 2 L squared, right? Then you just divide. So what you get is x bar is going to be equal to L cubed over 3 over 2 L squared. So easily that L cubed becomes L, and then you multiply by 2 over 3, so you get 2 over 3 L. So your center of mass is 2 over 3 L 0, 0. So on the line, it would be 2/3 of the way there. Then, when we solve for that, we end up with 1/3 because m is equal to, this results in 0. When you plug the things in, you get 8 pi over m. Alright? And then lastly, we solve for m, and we get 4 pi. And so therefore, our z bar is 8 pi over 4 pi, which is equal to 2. And so therefore, our center of mass is at 0, 0, 2. So that's going to be right there. So determine the center of mass, but this time, uniform density, rho equals 1. Okay? Of the figure formed by the intersection between the lines y equals x, y equals 3 minus 2x, from 0 is less than or equal to z is less than or equal to 1 in the first octave. So x bar, y bar, z bar is our center of mass. So first, let's solve for m. Well, that's simple. It's just going to be integral from 0 to 1, okay? That's z. And then we solve for x. Well, y equals x and 3 minus 2x. Those intersect at x equals 1 and y equals 1. So the point is 1, 1. So for x, this is going to be our x. It goes from 0 to 1, first quadrant. And then this is going to be y. We're going to plug in the equations from bottom to top. So lower to upper, because in order of lower y value to upper y value, so that's going to be x, 3 minus 2x for those bounding lines. And then our density is 1, so we're just going to do dy, dx, and dz. This being the integral within this integral within that integral. Okay? And this actually evaluates to 3 over 2. The next one is going to be x bar. We're gonna solve for our centers of mass. So I'm just gonna leave this as D, our region, or three-dimensional space region, and that's gonna be x dv because there's no density, and that actually divided by m, right? And that's going to evaluate to 1/3. And then y bar is going to be that's going to be 4/3. Okay, and z bar that's going to evaluate to 1/2. Find the force acting on an object with mass m over ln of 3 seconds with a momentum p equals e to the t. Okay, well, our relationship between the force and the momentum is the force is equal to the derivative of p. Sorry, because p is represented using velocity, we're going to have to do this. The derivative of p with respect to time. The partial derivative of p with respect to time. Our force at ln of 3, at time ln of 3, right? That's going to be e to the ln of 3, which is just equal to 3 newtons. And we know p, momentum, is equal to mass times velocity. And then impulse, which is represented using j, is going to be equal to your change in momentum based on the acting force in the system. External to the system. My bad. Alright, the next question is a marble with mass 3 grams collides with another marble of mass m at rest with a velocity 0.5 meters per second. Friction is negligible. Okay. First question is, what must be the value of m if the first marble stops immediately after the collision? Now, you don't even need to solve for this. This is fairly simple. If they have the same momentum, right, then that means that they'll have that the other one will stop. It'll transfer all of its momentum in the other one. When will that happen? When they have the same mass. So you know the answer is obviously 3 grams. But we can also solve for it. How do we solve for it? Well, we'll do our conservation of momentum equation. P naught is equal to P final. Or M1 V1 initial, or just V1 I guess is what we'll do. And then we'll do V1 prime. Plus M2 V2 is equal to M1 V1 prime. This is for elastic collisions, by the way. If it stops, the other one keeps going. That's an elastic collision. If it's inelastic, then that means they stick after collision. Plus M2 V2 prime. Okay. You can use this exact same formula if they're if it's an inelastic collision as well. It's just that M1 and M2 will be the same, so you bring them together, right? So you can take that out, and then you're left with V1 prime plus V2 prime. But since if it's inelastic, that's going to be in the same system, right? So V1 prime plus V2 prime is just going to be the same as just the velocity of the system, right? So you would just refer to that as V prime, I guess. Right? V1 plus V1 prime is equal to V2 plus V2 prime. That's our elastic collision formula. So as a result, we get V1 is equal to V2 prime. So the speeds are the same. Well, the speeds are the same. That means that the masses have to be the same. So therefore, we can conclude that, obviously, the mass has to be 3 grams in order for the first one to stop and the other one to keep going. What I'm going to go over is moment of inertia. This is also integration, and I also took concepts of multiple integration from multivariable. It's the same sort of thing as the moment of mass, the center of mass, except you don't divide by the total mass, which you derive through the same thing. I'll show you how it's done right now. So you, if you're an AP Physics C student and you haven't taken multivariable calculus or required that as a prerequisite, then you might have learned how to do this using a line integral. So that's going to be the integral over some curve C of r squared dm. Okay, that's going to be your line integral, and then you're going to try and solve for dm in terms of r, so that you only have to do it in terms over one curve, r. However, it's actually a lot easier if instead of doing it as a line integral, you do it as a multiple integral, depending on the number of dimensions. So we're going to say that it's going to be I is equal to, we're going to do this, our 3-dimensional integral over the space D of r squared dm. So it's the same thing, right? Except now we're over 3 integrals. Okay? And dm can become some value dA, some value dV, so on and so forth. And we don't try to solve it in terms of r or anything like that. Okay, we're going to leave it in terms of multiple integral. It's actually going to be a lot easier like that. Unless for you, you want to solve it in the way that I'm about to do it right now. But you would do that for all dimensions, which would be a major pain. So for all of these questions, they're going to be uniform on my practice ones, because we did a lot of the non-uniform ones for the center of mass. So we're going to make it easy for us on the integration for these questions, and we're going to do uniform densities. All right? So a uniform thin rod, so 1 dimension, with mass m and length l, is rotated about an axis at 1/3 of its length. Okay? At 1/3 of its length, it's rotated around there. That's not 1/3, but it's okay. So this right here is going to be a 0 point. So this is 2L over 3, and this is negative L over 3. So that's our region of integration. We only have 1 dimension, so we only need 1 integral. So in this case, this is going to be the integral from negative L over 3 to 2L over 3. And then we're going to plug in r squared. We're going to solve for dm in terms of one dimension, so that's going to be what? dr, dx really. But in our case, we're just going to make it, well, dl, right? One dimension dl, okay? But r is also in the direction of l, so r and l are essentially the same thing. Okay, we'll say that r starts here. This is r. That this is r, and then this segment right here, that's dr. Sure, let's go with that. What we do know is that with the uniform density, lambda is going to be equal to m, the mass, over L, right? But that's also equal to dm over dl, or dm over dr, I guess. Right? So when we're solving for dm would just be equal to lambda dr. So we just plug that in there. So that's lambda dr. In this case, lambda is m over L. We can bring that out. Those are constants. Is equal to m over L. Integral from negative L over 3 to 2L over 3 of r squared dr. Okay? And then what we end up with is that gives us 7 over 81 ml squared. Not going to go through all of the steps to integrate. We've done that plenty of times, and I'm sure you already know how to do an integral by now, especially a single integral. Relatively simple. Next one is a uniform square sheet in the xy plane of mass m and side length s is spun at its center. Determine the moment of inertia. Okay, so 2 dimensions, that's going to be 2 integrals in 2 directions. In this case, it's going to be dx and dy, but, well, it's going to be dx and dy, right? So, because it's in the xy plane. So what is our region? Well, it's in the center, right? So right there, it's our region. There's no formula for this, right? We're not given a graph or anything like that. So and it's uniform. So we can just say, well, it's negative s over 2, because the side lengths are s. Negative s over 2 to s over 2 for both. To s over 2, right? Negative s over 2 to s over 2 for both, because it's square. Spun at its center. A lot easier than the last one at 1/3. It gives you a weird number for the last one, 7 over 81. This one is going to be very easy. Just plug that in. You have r squared dm, right? Well, in this case, sigma is equal to m over a, right? M over a being s squared, because the area of a square is the side length squared. And that's the same thing as dm over dA. That means that dm is equal to sigma dA over the surface region S. Instead of writing the distance thing again. R squared sigma, that's just m over s squared. We can take that out to the front. dA. We can do dx dy or dy dx. It doesn't matter because they're the same bounds. As a result, this integral evaluates to 1/6 ms squared. That is it for our mechanics review. And so hopefully you have gotten a bit more practice in and you're more well prepared for that exam that's coming up. And I'll put the link to this document right here that has all of those questions that we just went over, as well as the solutions and how to solve them, and the questions as well, in case you couldn't hear me recite those questions, or you're more of a visual learner, then there you go. But there might be more information as to what I'm saying outside of the material here. It would be a lot easier to understand, especially the multivariable stuff. And a lot of times I don't even solve the information here. And with that, I wish you guys good luck.